Hey everyone, in this AP Chem series video, we're going to talk about metallic bonding. First, remember that there's lots of different types of solids like molecular, ionic, metallic, and covalent network, and each of those is made of particles held together by a different attractive force. In this video, we'll take a look at the intramolecular force that holds metallic solids together, known as metallic bonds. Before we take a look at metallic bonding, let's rewind a little bit and talk about a type of intramolecular bonding that you're a little bit more familiar with called ionic bonding. In ionic bonding, you've got metal atoms that are going to transfer their valence electrons to non-metal atoms. This forms oppositely charged ions that are then going to be attracted to each other. We can see that here with my metallic sodium and its one valence electron that it wants to give up and lose to achieve a stable, low potential energy state. It's going to transfer that valence electron to the bromine atom. The sodium now has a +1 charge, the bromine now has a -1 charge, and they're going to be attracted to each other because of those opposite charges. So now let's ask the question, what would happen if there wasn't a nonmetal present like bromine that was willing to accept these electrons? In fact, what if the only other atoms present were other metal atoms? This might be happening in any sample of pure metal like a gold ring that's made of only gold atoms, or more applicable to this example, a chunk of solid sodium that only has sodium atoms. This is where metallic bonding starts to come into play. Let me enhance my model by adding some additional sodium atoms, each with one valence electron that they want to try and lose. So with metallic bonding, you've still got metallic atoms that are trying to lose their valence electrons, but the difference is those valence electrons don't really have anywhere to go. Instead, those valence electrons become delocalized from their original atom, and then they become free-flowing amongst all the other metal atoms in the sample. This is one of the key ideas for the video. Make sure to take some time and write that down. Let's add this description into the model by showing each valence electron being removed and each sodium atom attaining a +1 charge. The only element missing from this model right now is the fact that these electrons that have been lost are free flowing. That means they are now free to move in and amongst all of the sodium atoms in the sample. Here's a more accurate version of what this might look like. Let's label some of the key features of what's happening. First, notice we've got the electrons that are now free-flowing in between the atoms in the sample. The metal atoms have become cations. That means they're positively charged, and they have fixed positions. That means they do not move. Only the delocalized electrons are free to move. Because those electrons are free to move and flow within the sample, this is often called the sea of electrons theory. So that's how it all works, but we should close by saying then, what exactly is a metallic bond? The metal cations are held in place by their attraction to those delocalized valence electrons that surround them. I like to think about the delocalized electrons almost acting like a sort of glue. The positive metallic cations aren't attracted to each other, but they are attracted to that space surrounding them, which is negative because of the presence of those valence electrons, and all of the atoms get held in place as a result. And that concludes this video on metallic bonding. Thanks a lot for watching, and here's a brief summary.